Okay, so why is this important? Well, the ring is actually useful for deriving other results that we'll be running into quite a bit over the course of the semester. One situation is the electric field of a uniformly charged disk. Put that down here. So let's say you have a circular disk, say a piece of plastic or something like that, and again, it has a radius, and we're putting it in the XY plane. And Z is coming out. Only now it's solid. Okay, so this is a kind of hard to draw, indicate it, but it's a solid disk, and it has a uniform, again, we'll say positive charge spread over the entire surface. And we want to do the same thing. We want to calculate what the electric field is, magnitude of the electric field at some location on the z-axis. Okay? What do? Where can we start here? What's the general procedure? The procedure is we break into pieces, right? Break the charge distribution into pieces, each with a size of charge delta Q, and then draw the delta E. Well, in the previous cases, we've been breaking it up into pieces that have looked like point charges, but what might be a better choice in this case? We could break it up into concentric rings, couldn't we? We could say this disk is nothing more than just a series of concentric rings, okay? And if we look at one single ring, and I'll try to color it in just so it's a little easier to see. Let's say we look at one slice, one thin ring out of this disk. Here's a thin ring that's positively charged. The electric field due to that ring is pointing in what direction at that location? In the positive z direction, right? Along, same as it was in that case, right? So that's our delta E. So what am I going to get? When I add all those up, what am I going to get for my result? The electric field is going to be pointing in the positive z direction because all the delta E's are going to be pointing in the same direction. So we get a situation that looks like this. We can just model the electric field, model the disk as a series of concentric rings. So here's ring number 1, and you probably can't see it, but there's a tiny little electric field at the origin there, at the observation location. Electric field number 2, and we keep adding up the delta E's, so there is delta E2 plus delta E1 gives us our total delta E so far. Ring slice number 3 increases the electric field, then slice number 4, slice number 5, 6, 7. We keep on going and going until we get, it goes off the screen here, but we get a uniformly charged, positively charged, in this case, ring, where the electric field for each little slice is pointing directly away. Okay, so that makes it kind of easy to visualize. What about actually doing the calculation? Well, you have to go through the same steps. We've picked our delta Q. We then have to write delta E in terms, or write an expression for delta E. I guess we should say more generally, write an expression for delta E. And when you're doing it analytically, we said it's often in terms of the integration variable, right? So let's look at this disk. We have a disk that has a radius capital R, And there is one little slice of this disk. And this little slice is not, could be any distance away, right? So this little ring is, we'll call little r to indicate the radius of the particular ring, not capital R, the total radius of the disk. Okay, and then we have Z. So what's the integration variable? What changes as we move from one ring to the next? Which R? Little r. Little r is the thing that's changing, right? So we're going to write a summation in terms of little r, okay? So we have the electric field. Really, it's just the Z component, but that's the only component we have here. Delta E is equal to 1 over 4 pi epsilon 0. Delta Q, which is the charge of the ring. Q is the charge of the whole disk. Delta Q times Z over is it capital R squared plus Z squared to the 3 halves, just like in the formula for the ring? It'd be little r. Wouldn't it be little r? Because we're looking at the electric field due to one of its little slice, one little piece of that ring. Okay, so we're not. If I use capital R, that would tell me a ring right at the outer edge. But we want a variable here that's going to be changing as we move from one ring to the next, right? So that's our expression. We want a delta Q in terms of delta R. This requires a little bit of geometry here. We have to think about the number of, or the area of the disk is equal to n times the area of a ring. And the same would be, or we can say that the total charge is equal to n times delta Q. So as usual, if we can figure out this relationship, we can then do a division and then figure out delta Q in terms of delta R. So what's the area of the total disk? What's the area of a circle? Pi r squared. So I would say the area of a disk is pi times which r? The area of the entire disk would be pi times big R squared, right? Okay. How do we figure out the area of a thin ring? Any ideas? There's nothing inside here, so it's just the area of this little slice, right? Okay, the area of the outer circle minus the area of the inner. That would work. Let's see if we can do that. We would have pi times r squared, or let's do it this way. Pi times r plus delta r squared. If I say that this is r and this is delta r plus delta r, we're going a little bit farther out as we go from one to the sort of the inner radius to the outer radius. Minus pi r squared. Okay, that could give us the area of the slice. Okay, of that ring, and it's a little bit tricky because we already have pi r squared. There's a lot of algebra here. R squared plus 2r times delta r plus delta r squared minus pi r squared. Well, let's see. The pi r squared is going to cancel out. And then we have 2 pi r times delta r plus a pi delta r squared. Well, it turns out that this term kind of goes away. And the reason is because you have a delta r, which is a tiny little number. If you square a tiny little number, you get an even tinier little number. So really, it's only this term that matters. And the way you can think about this is you have the circumference, 2 pi r, the distance around, times the thickness. So we have a length times the thickness giving us an area of that thin ring. Okay. So really 2 pi r times delta r is the area of the ring that we want. And so I'm sort of hand-waving around this, but it's just making sort of an approximation. So we have pi r squared then is equal to n times 2 pi little r times delta r. And we have then q is equal to n times delta pi, or delta q. So we can say then that q over pi capital R squared is equal to delta q over 2 pi r delta r, or delta q then is q over pi r squared times 2 pi little r delta r. And we have a pi that goes away and a factor of 2 here, so we have 2q over r squared delta r. Okay. We finally go through all that geometry. We can then plug that back into the formula and do the integral. Okay, and as usual, I'm not going to do the integral. I'm just going to give you the result. We have an integral of, a little more room here. An integral from 0 to what? Big R, right? We're going from the center to the very outmost edge. 1 over 4 pi epsilon 0. We have 2 capital Q over little r, or excuse me, over r squared, capital R squared. I lost the little r here. There's a little r here. So we have Q little r in the numerator. We have a z in the numerator, and we have r squared plus z squared to the 3 halves. Okay, so it looks pretty ugly. But a lot of stuff is a constant. Basically, all this is a constant, and the z is a constant. So you're integrating r over r squared plus z squared to the 3 halves. You do that integral, you end up with a rather ugly-looking expression, which is q over a, and I'll tell you what a is in a second, divided by 2 epsilon 0 times all this stuff in parentheses here. Let me get rid of this. 1 minus z over square root of capital R squared plus z squared, where a is the area of the disk, and the area of the disk we said is pi times capital R squared. Okay. So this expression here is the electric field, the magnitude of the electric field of a uniformly charged disk. And again, we're on the center axis. Distance z away, radius capital R.